Welcome to our first module, which is dedicated to linear algebra, which is a mostly recap and an introduction to quantum algorithms. In this section, today we'll talk about linear operators, and we'll focus on three things: projections, adjoints, and the computation of eigenvalues and eigenvectors. So this is completely a recap, but we will talk about linear operators represented by their matrices. And so matrices are arrays of size m by n in the most general case. In our, if we will focus on entries in the complex numbers, okay, and so the matrices are equipped, the space of matrices is equipped by first an addition. So for example, that addition works coordinate wise. So for example, if I have the matrix with all ones plus this matrix, then coordinate by coordinate, I realize an addition. So this, I consider it to be a prerequisite in this course, okay? So I'll just go over this very quickly. Likewise, there is a matrix multiplication. The dimensions have to be compatible, meaning that an m by n matrix can be multiplied by an n by k matrix. And then every entry of the matrix multiplication is going to be the dot product of the ith row of the matrix A with the jth column of the matrix B. Hence the constraint that those two elements need to have the same size. Otherwise, that dot product simply isn't defined. Let's just work this out on an example, although like I said before, like matrix addition, matrix multiplication is considered a prerequisite in this course. So the matrix A here, I will write here, like this. And then the matrix B, I like to write them here to facilitate the calculation of each coefficient. And this is my matrix A times B. And if I want, for example, this coordinate, I will do the dot product of this vector and this vector. And it means I multiply those two coefficient, add them to the multiplication of this two coefficient, and add them to those two coefficient, and the answer is 2, okay? And if I continue like this, I'll have 2 here, and I'll have 0 here, and another 0 here, okay? And this is the matrix multiplication. So here I'm going admittedly very fast because, like I said, these are prerequisites. So the matrix vector multiplication is just an extension of the matrix multiplication procedure, where the vector here, the column vector, is considered as an n by 1 matrix. And then this is also a linear map from C to the n to C to the m, where we associate to the vector v. We will consider that this is A times D, okay? Another example here, we have that A times V is 1, 1, 1, 1 multiplied by 0, 1. Notice the way I like to present them. Not everybody does it. And then you have here a 1 and another 1, okay? And that's this entries give you a linear combination of the columns of A that you have in your answer. Okay, now we've seen briefly outer products in the lecture dedicated to vectors, and now we'll go back to it because this will have a lot of importance for projection operators. Okay, also an outer product is a matrix multiplication, and the result of that is also a matrix. So here we assume that we want to multiply two vectors, a bra and a ket. Now the inner product was pretty much the matrix multiplication of the bra by the ket. The outer product is going to be the matrix multiplication of the ket by the bra. Okay, so what do we have here? We have this multiplication, and if you follow the rule of matrix multiplication, then you'll see that the entry ij is going to be xi y star j, where y star is the complex conjugate of y. Okay, so this is simply taking the the matrix product formula and apply it to the multiplication of the n by 1 matrix, which is the ket, by the 1 by n matrix, which is the prod. Some examples here. So like we said before in the vector lectures, when you have the canonical basis and then you take the outer product of the canonical basis, what you get, for example, if you multiply 0 by 0, what you get is a 1 in the first coordinate and zeros everywhere. Likewise, if you do 1 by 0, what you have is a 1 in the second coordinate, okay? And in general, ij will give you a matrix with zeros everywhere, except for the matrix that corresponds to the row number I and the column number j. And then if you write that down in c to the n, what you're really writing down is simply the identity matrix, okay? Now, moving on to projection operators. So we're going to make use of those outer products to perform a projection onto a certain subspace. Okay. Now, to do this, we have to assume that we have at our disposal an orthonormal basis of that subspace, and I refer to our previous lecture for the definition of that, and most importantly, how to compute an orthonormal basis from a given basis of the given space. Okay. So all we need to know here is that they're both all the vectors in that basis are orthogonal to each other, and they all have norm 1. Another thing that we may want to keep in mind is that once you have an orthonormal basis of, say, a dimension k subspace of c to the n, this can be completed into an orthonormal basis of c to the n. And the importance of that, of course, is it makes it a little more natural to see what the projection is doing. So we assume that we have psi 1 to psi k, okay? And let's, for the sake of the argument, assume that we have a basis of c to the n. So let's say c to the n is spanned by psi 1 dot 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 until psi k, and then there is a psi k plus 1 outside of our span and actually orthogonal to it, of course, until psi n, okay? And we're going to project onto the span of just these vectors, okay? And what I claim here is that the projection, so the matrix that's going to perform this projection, is basically given to us by the sum of the outer products of the psi I for I ranging from 1 to k. Okay, so assume that you have an input vector, x, which is given by x1 psi 1 plus dot 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 plus xk psi k plus xk plus 1 psi k plus 1 plus dot 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 until xn psi n, okay? And, well, the projection onto the subspace spanned by the psi 1 psi k should be exactly this. And what do we get when we take p of x with the p defined as we just did? What we have is precisely psi 1 times the inner product of psi 1 and x plus dot 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 until psi k times psi k inner product with x. And as we've seen from the decomposition onto an orthonormal basis, this is basically x1, and this inner product, for example, is xk, which gives us exactly what we claimed. Okay, so those outer product here they give us exactly what we need to perform our projection onto that dimensional K subspace of C to the N. Now, let's see how it works on a few examples. So if we have our space generated by just the vector, the first vector of the canonical basis of C2, then what we're doing is we're mapping x, which is x1, 0, maybe I should call it 0 here, that would be wiser, plus x1, 1, and it just maps it to the vector x0, 0, okay? Now, this maps x, this time, to x1, 1. Now, if you have vectors in C4, then what happens is you're going to map x, which is given to you by x0, 0, plus x1, 1, plus x2, 2, plus x3, 3. You're going to map this to x0, 0, plus x1, 1. And now, slightly more complicated, let's assume that we have psi1 and psi2 given by these vectors here. Then what we have is we will map x to the vector 1 over square root 2. So 1 over square root 2 x0 plus x1 times psi1 plus 1 over square root 2 x0 minus x1, and you can verify that by expanding those products, okay? So now transposition and conjugation, which is what we need to define the adjoint operator. So assuming you have a matrix that is m by n, then, well, you already know what the transpose is, which is when you take the ith row and then you turn it into the ith column here, okay? So transposition is something that I assume is already known here. And then the conjugation is simply taking the complex conjugate of each of the entries of A, okay? And transposition and conjugation gives us what is called the adjoint operator. And the property of the adjoint operator is whenever you have the inner product of x1 by a times x2, then it's the same as saying the inner product between a adjoint x1 and x2, basically, okay? And the one class of linear operator that's going to be extremely important is unitary matrices, okay? So for reasons that will become more evident when we will be talking about transformation of a closed system, a closed quantum system, unitary matrices are extremely important so that we can describe everything that we need in quantum algorithms, okay? So, but for now, all we need to know is what is the definition, okay? So unitary is the inverse of your matrix is its adjoint, okay? And there are very important unitaries, for example, the Pauli matrices. So you can verify that all of these matrices that you see, the identity and the matrices X, Y, and Z, they all have the property that when you multiply them by their adjoint, you retrieve the identity, okay? And these are extremely important for quantum computing. Now, to finish, we'll talk about eigenvectors and eigenvalues. So eigenvectors are the vectors so that when you apply to them the linear transformation, you get a multiple of the vectors. So for example, you say a times x equals lambda x for lambda, a complex number, okay? So how do you calculate such a value lambda? Well, you can solve for determinant of a minus lambda I equals identity, equals 0, and that's because the vector, which is an eigenvector, so that satisfies this equation for a given lambda, is necessarily in the kernel of the matrix A minus lambda I. So because there is a kernel, the determinant has to be 0, okay? So the first step to calculating eigenvalues and eigenvectors is first solve for lambda. So you calculate the lambdas and then solve a psi equals lambda psi for each lambda, okay? Where we find the coordinate of psi in a given basis, typically the orthonormal basis, the canonical basis, okay? So let's work this out on an example. Let's say A is the matrix. Sorry, that is not what I wanted to do. Let's say A is this matrix. Okay, now so the determinant of A minus lambda I is equal to what? It's equal to minus lambda 1, 1, minus lambda, and that is lambda squared minus 1, which is lambda minus 1, lambda plus 1. Okay? So the eigenvalues are lambda equals 1 and minus 1. So let's find the eigenvectors corresponding to lambda equals 1. Okay? So we assume that we have V equals x0 times 0 plus x1 times 1. Then what does this look like? A times V, we assume, satisfies A times V equals 1 times V. Okay, so what do we have here? What we have is A times V is going to be x1, x0, and it has to satisfy that it's equal to x0, x1. So this forces x0 to be equal to x1. Okay? So what does this mean? That means that V equals x0 times the vector 1, 1. Okay? Now, on the other hand, what if we want to find the vectors that satisfy A times V equals minus V? So what do we have here? We have that it must be that x1, x0 equals minus x0 minus x1. So this forces x0 to be equal to minus x1, okay? So what we have is that V equals x0, 1, minus 1. And so what we have is that the eigenvectors for lambda equals 1 are the span of the vector 1, 1, while the eigenvectors for the eigenvalue lambda equals minus 1 is the span of 1, minus 1. So this concludes the sort of quick recap on linear operators. Of course, we only barely scratched the surface, but some of those things were considered prerequisites, and a lot of other things won't be absolutely necessary to study quantum algorithms. One of the important points in this lecture was also to make you guys manipulate the vectors in the Dirac notation, especially those outer products, because we've already seen projections, But here, we really want to see everything in terms of the Dirac notation to get familiar with it for when we casually use it when describing algorithms in modules 2, 3, and 4. Thank you for your attention.